Okay, here we go. So kind of an appropriate level of suspense as we went to lunch, right? We have this function. It's the radical function shifted to the right. We know it's increasing at a decreasing rate, starting at 2.0. So let's do one more thing before we get into the derivative. Let's talk about the domain of the function f, okay? It starts at x equals 2. So it's the set of all x such that x is greater than or equal to 2, right? That's where the graph lives. For all values 2 or greater, the function is going to have an output, a y value. Piece of cake. All right, so now we're trying to find the derivative function. We set it up like this. The function's name is f, so we set it up like this. Now, since we've created the equal sign and we have the limit, we keep both of those all the way through to the end until we evaluate the limit, and then we just keep the equal sign. This is where it becomes very function specific, right? So the first part, and this is where pre-cal is right now without the limit, we have to set up our function and replace x with x plus h, yeah? Now our function is a little bit easier than the quadratic trinomial, which had 2 x's in it. This one only has 1 location. So this becomes the square root of not x minus 2, but x plus h minus 2, all right? Minus, now we set up the second term, which of course is just f of x. And so that's just the function itself, square root of x minus 2. And it's all over h. Now, if we can evaluate this limit, bless you, we will have ourselves a derivative function that will give us the instantaneous rate of change of that graph, or anything that can be modeled by that graph at any singular value of x. Well, let's try direct substitution, right? Never not first. We have a limit. You plug in a 0 for h, you get the square root of x minus 2 minus the square root of x minus 2. That's 0 over 0. So I'm going to put 0 over 0 there. Now, at this point, 0 over 0 is nice. Because not only does it mean we get to do more math, but that means we set it up correctly more than likely. Because remember, h can't be 0. Because that's a single moment in time. And you need 2 points for the slope. Now, the bad guy in the bottom is h. We know that if I can somehow divide out the h, I can then use direct substitution to find the location of the hole where h equals 0 is. There's 2 terms in the top. They both have an h in it that I can just conveniently factor out? No. So what method did we learn to do this in 1.4? Ratcon, yeah. So rather than teach the method as it arises, we've already practiced this. So we're going to multiply by the square root of x plus h minus 2 plus the square root of x minus 2. It's a little bit of writing, but at least we know how. Plus square root of x minus 2. And we show that. Working straight down again, we get equals, the limit as h goes to 0, all over. Now, I'm going to put the bottom first. The bottom, remember, we don't, on the side that doesn't have the radical, we just rewrite it. We keep it factored. So it's the square root of x plus h minus 2 plus the square root of x minus 2. We leave the h factored. In the top, we have 2 conjugates. We multiply them together, the middle terms will cancel, right? So really, we can just look at the first and last. Radical times radical is radicand. So that's x plus h minus 2, okay? I don't need parentheses around x plus h minus 2 because it's just 1 in front of each of the radicals. But look what happens here. Now it's minus, so I do have to be careful, minus radical times radical, in this case, is radicand. You either put minus and then parentheses, the radicand, or you distribute the negative to both terms in the radicand as you write it down. Yeah? But that's where like a careless mistake, bless you, can just, take advantage of you. All right, now if we've set it up right and if we've retconned it correctly, as we continue to simplify, everything in the top that doesn't have an h should cancel. So let's see what happens here. I'm kind of out of room. Well, I don't want to highlight it. I'm going to move this over. And remember, we just start a new column. Yum. So equals, the limit as h goes to 0. And let's see if we can evaluate the top. Let's distribute this negative while we write things down. What's going to happen with the x's? Will they cancel? Yeah, x minus x. They're gone, okay? What about the negative 2's? -2 minus -2 is 0, right? Because that's -2 plus 2. So that takes care of, what are we going to be left with then? Just an h, a positive h, right? I'm going to come over here and just put a positive h all over h times the square root of x plus h minus 2 plus the square root of x minus 2. A little bit of writing, but man, that's good algebra. And now, those divide out, leaving a 1. All right, so here's where the limit takes care of the division by 0 problem. We're going to now direct substitute a 0 in there as if we were dividing by 0, but we're not. We know algebraically we've remedied it. We're finding the y value of a whole by finding the y value of a graph that paves right over it. All right, so any h that's left now becomes 0. And when we plug in, we don't need to write the limit anymore. Well, there's only one h that's left. It's right here. So I end up with the square root of x minus 2 plus the square root of x minus 2. Well, one of those plus one more of those makes 2 of those. Yeah. So if you want to write that another step in between there, you can. Now, notice I have the equal sign there. I haven't been bringing down the left side, but I think now is a good time to bring the left side back down. Congratulations. We just bless you. We just found a function that will give us the instantaneous rate of change, or the slope of the tangent line, or the slope at a point of the radical function square root of x minus 2 for any singular value of x. It's almost like it's the velocity function for our graph. It tells us how fast it's rising. Yeah? Now, let's look at one thing here. Well, I'll kind of hang back a little bit. Sometimes I get ahead of myself and I'm like, you already wrote questions to take care of that, sir, B, C, and D. All right, so let me hang back a little bit. No, let me not hang back. I want to do what I was going to do, dang it. You can't tell me what to do, self. Let's find the domain of f prime, okay? That's what I wanted to do. Well, just like on the original function, right, I have the square root of x minus 2. I can't take the square root of negatives, right? So that's why any value that's smaller than 2 is going to give me a negative. They're off. That's a whole slew of values, right? Same thing here. I still can't take the square root of a negative, so I can't use any value smaller than 2, right? 1 minus 2 is a negative, 0 minus 2 is a negative. But notice how the radical jumped from the numerator, where 0 is okay, to the denominator, where 0 is not okay. What happens if I plug a 2 into the derivative? I get division by 0, right? Can we divide by 0? Are we Newton? No. So the domain of the derivative is the set of all x such that x is strictly greater than 2. Yeah. You'll always find that the domain of the derivative is either the same as the original function or possibly smaller. Okay? So remember I said that a function is differentiable if the derivative exists? The derivative does not exist at 2, but the function does. And we've already seen why. In the very beginning, I told you that since the square root of x, or x squared, has a horizontal tangent at the origin, its inverse has a vertical tangent there. So if you were to draw the tangent line right there at 2, we get a what type of tangent line? Vertical tangent line at x equals 2. What's the slope of a vertical line? Not 0. Remember, 0 is the slope of a horizontal line. It's the other one. Just think about going skiing. You've never skied before. I've never skied before. I need to practice skiing. Okay, you're going to practice on the level 0. It's the basic level, right? You're not going to start on level 2. You're going to start level 0, and that's not even skiing. That's just called walking, right? You're on a flat surface. Now, if you get really good, you ski like a level 10 slope or a level 100 slope. Now, can you ski down a slope that is infinite? That's what a vertical line slope is. It's either infinity or negative infinity. Can you ski down that? No, it's right. Very good. It's called falling, right? Free falling. Yeah. Free falling. Yeah. So this is cool. The function exists at 2, but the slope doesn't, and therefore the derivative doesn't. Pretty interesting. Okay, now let's go ahead and try out this new handy dandy function. Find the slope of the function at x equals 6. Well, now that I have that function, I could just say f prime of 6. We always, denote it on the other side. And then I plug in, and I get 1 over 2. Square root of 6 minus 2 is 4. And square root of 4 is 2. I get a fourth, right? Yeah, so, wow, that's cool. I know that somewhere over here at x equals 6, we'll call that 6. At that instant, that graph is going up 1 for every 4 it's going to the right. Or it's going up a fourth for every 1 it's going to the right. Now, if you think about the slope as being 1/4, at that moment, this is where we kind of later on get into vector calculus, right? The numerator is the change in the y, and the denominator is the change in x. So at this point, there's more horizontal movement, 4 times as much horizontal movement as there is vertical movement, right? That means it's pretty flat. Same thing here. What is f prime of 16? Well, let's plug it in on the left side, and we get 1 over 2 times the square root of 16 minus 2 is 14. Wow. So, yeah, that's a great answer. But it's going to be smaller, right? I know it's going to be smaller than 1/4. So my y values are getting bigger, but what can you clearly see now is happening to your slopes? F prime of 27 is going to be 1 over 2 times the square root of 27 minus 2 is 25. That's 1/10. That's smaller than this one, right? I think I probably intended that to be an 18, right? Let's change it. I'll change it. Let's change that to an 18 so we can compare apples to apples. 18 minus 2 is 16, right? And the square root of 16 is 4. 4 times 2 is 8. So that's what I want you to kind of see. As we go from left to right, our derivative values, our slope values, our instantaneous rate of change values, as x increases, they're getting smaller, right? A fourth, an eighth, a tenth. Well, we already do that. The y values are getting bigger, but the slopes are getting smaller. That's why the function is increasing at a what? Decreasing rate. Yeah. And now we already let the cat out of this bag, right? So what is the derivative at 2, which is the genesis point for the domain? Well, f prime of 2 is going to be 1 over 0, which means it's undefined, dne. And it's some type of infinity. It's really hard to tell if vertical lines have a slope of infinity or negative infinity. Okay? It's really a matter of whether you're falling down or falling up, right? Which is like, how can you fall up? Believe me, it can happen. I stand outside sometimes, and that last step coming up the stairwell can be a tricky one. And I see people falling up into the 900 wing all the time. And I always feel bad. I kind of walk over there and just, it's okay, brother. I do it every day on accident, because then they're like, I meant to do that, right? I meant to do that. It's okay. It happens. We're all human. Yeah, pretty cool. So let's go ahead and look at part C. Describe now the values of x for which the function is I continuous and I differentiable. Okay. Well, this function is going to be continuous everywhere it starts, yeah? It's not going to be continuous over here where it doesn't even exist. Will the function be continuous at 2, the left endpoint? Can we have a function continuous at a left endpoint? Yeah, remember we talked about it in 1.5. As long as the limit from the only side you can approach it equals the function value there. If the graph dead ends into the function value, does it? The limit from the right is 0 and the function value is 0. So yes, we can make exceptions for the 3-step definition. So we'll say in a complete sentence, part I, f is continuous. Do you want to use math symbols or right words? Well, that's for there exists. This was the upside down A. F is continuous for all x greater than or equal to 2. Or you could say F is continuous on the interval x epsilon beefy bracket 2 comma infinity. Either one. And instead of the upside down capital A, you can write the word for all. It's essentially one is an inequality and the other is an interval. Beat the bot, right? Now, where is it differentiable? Is it the same interval? Remember, differentiable, if you come up here, means the derivative exists. It's differentiable at a point if the derivative exists. Does the derivative, also known as the slope, right, exist at 2? No, it doesn't, okay? So for part II, you'll say F is differentiable, which again, I abbreviate diffable. If you're going to use the same notation, you can say for all x strictly greater than 2, or you could say F is differentiable on the interval x epsilon parenthesis 2 to infinity. You'll never have a domain for the derivative be larger than the domain of the function. It's either going to be the same or smaller, okay? So this kind of gives us a way to determine. If you're not sure where a function is differentiable, all you got to do is find the domain of the derivative, right? A function is differentiable over the domain of the derivative. So I'm going to write that. I'm going to come back up here above the box, and I'm going to say a function is differentiable. That's just going to be the domain of the derivative, f prime, okay? Now, moving forward, we're going to be looking at different places where we can visually spot a function being not differentiable. And we already just found one of them, right? At any vertical tangent, not vertical asymptote, at any vertical tangent, the tangent line exists, right? Because a vertical line exists, but its slope does not, right? We don't call it slope. It has no slope, right? Back in the day when I taught Algebra 1, you know, we said this, right? No slope, to help them remember. They couldn't handle like the idea of infinite slope. And then the other one would be this, 0 slope. So Mason, if you latch onto that instead of the ski analogy, it might help, you know. Oh, you got it. Oh, you ski. Oh, okay, yeah. Well, I'm just saying vertical lines have infinite slope or no slope, and horizontal lines are 0 slope. You're just in the splash zone, so you're getting wet with math all the time. All right. You're gonna go with that, are you? What? Yeah, you're looking around. Yeah. Joke opportunity, right? No, I know. I saw it. He's looking around. Should I go for it or not? You should have gone for it. Write the equation. Write the equation of the tangent line in Taylor form at x equals 27. All right, so let's go ahead and just change this 6 to a 27, right? It's not drawn to scale. What I want to do is I want to write an equation of that tangent line. There's a lot of reasons why we want to write an equation of a line. Lines are a lot easier to work with than curves, okay? And whether they're polynomial curves or exponential curves or transcendental curves like sine and cosine and e, we can find tangent lines. And lines are always mx plus b, much easier to work with. And you'll see later on, another advantage of lines is like if I want to find an approximation of, let's say, this red curve somewhere other than 27, notice that in the neighborhood of 27, there's just like a small radius that I can go left and right where the red line's function value and the tangent line pink function value are pretty similar, right? They're pretty similar. Now, they diverge pretty rapidly, right? As I continue going to the right, they start separating more and more. But hey, in the neighborhood of 27, the tangent line's y value is a decent approximation of the function's y value. which may be really hard to compute or maybe even impossible to compute. If you've been in economics and you've heard the term marginal, whatever, marginal cost, marginal utility, marginal profit, marginal revenue, anytime you say the word marginal, you're projecting out along a tangent line. Did you know that? So at this current production level of 27, the slope of the line is the marginal projection because it's something per unit. You're using the slope of the line per one. That's pretty cool. So you can project using the tangent line without having to actually produce something. All right, so here's Taylor form. We'll revisit Taylor form again later in the year when we study Taylor polynomials. Right? Yeah, we got 5 minutes. So equations of lines, equations of lines. There's lots of them, right? Y equals mx plus b is still a dandy of a form, right? That's your slope intercept form. Okay, because your slope is visible, m, you know, and then your y-intercept, you have to know which intercept it is b, right? And there's lots of different versions. So if you have that memorized, I'm not going to tell you to unmemorize it. But here's what we're going to be using. We're going to be using Taylor form. And it's named after an English mathematician by the name of Brooke Taylor. And here's what it is. It's kind of like point slope form, except it's solved for y. It's y equals the y value, y sub 1, plus the slope times x minus the x value. Boom. Okay. And what it does is it uses, let's go ahead and write. You need a point, x sub 1, y sub 1, and then you need a slope, m. You need a slope at that point. Well, guess how we're going to find the slope of a curve at a point? Slope at a point, slope at a point, slope at a point, slope at a single point. That's the derivative. Yes, the slope at that point is going to be f prime of x sub 1. Okay, there you go. We can use calculus. So really, if we ever need to write the equation of a line, all I need is the equation of the function and an x value. That's all I need. I can plug the x value into the function to get the y value, and then I can find myself a derivative function and plug it into the derivative to get the slope value. And now that I have my point and I have my slope, I can plug it into Taylor form. Taylor form is good because it writes things in increasing order. Okay, whereas mx plus b is in decreasing order, right? You have your linear term, x to the first, and then you have your constant. Taylor form writes it in increasing order. So it starts with the constant, y sub 1, and then it builds up to the x to the first. All right? So memorize this. Memorize this. Now, to help you memorize it, just remember that slope in Algebra 1 is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, yes? Well, replace the y sub 2 with just y. Y minus y sub 1, x minus x sub 1. And now let's multiply both sides by x minus x sub 1. X minus x sub 1, x minus x sub 1. And what happens here? These two go, and we're left with y minus y sub 1 on this side. And over here, we're left with m times x minus x sub 1. This right here is point slope formula. Point slope formula. It's not solved for y. So all we have to do now is to solve it for y by adding y sub 1 to both sides. And when we do, we get y equals y sub 1 plus m times x minus x sub 1. So really, Taylor form just kind of comes from the formula for slope. Okay. Now, to finish it off, here's what we do. Let's get our points in order. 27, comma, and then if I plug it in, what's f of 27? Well, it's going to be the square root of 27 minus 2, which is the square root of 25. It's 5, right? So there's your point. And then what's the slope? We already found f prime of 27 to be 1/10. So now that I have my point and I have my slope, All I got to do is drop it into Taylor form. So y equals the y value, 5, plus the slope 1/10 times x minus the x value of 27. And that's it. That's the equation of the tangent line. We're going to be writing equations of tangent lines all year long, and every time we're going to be using Taylor form. All right, so what a great day. Quiz tomorrow over the formal definition of the derivative and the IVT question, all right? Remember to rock the vote and beat the bot.